This short video is just going to start off talking about the concept of method of joints. This is a mathematical tool where we use to calculate what the forces within each truss in a bridge are. So I've got an example over here of a bridge that has a number of trusses, X, Y, Z, A, B, C, and D, and it's got a number of forces acting on that particular bridge. Now, what I'm going to do is I'm going to say in the question we're looking for what are the values for the force within truss X and the force within truss Y. So what is the value of truss X or the force value of truss Y? And we know that forces travel along these trusses in a bridge. They don't travel across the trusses, they travel down those trusses through our understanding of forces. And so what we can see is we could do quite a complex calculation over here using all these different forces and stuff, but the method of joints says that if this bridge is not spinning or not moving up or down and is therefore in equilibrium, each joint in the bridge is also not spinning, moving up or down. So each one of these joints we could choose and isolate that joint and say it's not spinning, it's not moving up or down or left or right. And so each joint is in equilibrium as well. So when we're looking at X and Y, we see X and Y both come to this one joint over here. And there's one force over here that we don't know. And so we can simplify this entire problem by simply looking at one joint and isolating the problem. And that's the whole concept of method of joints. So what I'm going to do is take this whole bridge, instead of looking at the whole bridge to find X and Y, I just simply look at that one joint. And here it is. This is the joint that I'm talking about over here, and we're zoomed in. Here's my 270 Newton force that I came from my problem, and here's my member X and my member Y, and that's the degree angle of 60 degrees. And once you do that, the problem becomes quite a lot simpler, because all we need to do is say, well, we know there's a force that's acting along that member, and we know there's a force that's going to act along this member. So what I'm going to do is I'm just going to replace this member X with a force. I'm going to replace this member Y with a force. Now, I don't know necessarily that those arrows are correct. I'm just guessing at the moment. I'm going to calculate what they are. But I know that I'm going to have a force here and a force here and a force here. So effectively I've got a simple three-force system with one known force. And there's two ways you can solve this. The first is analytically, which basically means I'm going to use some maths. And if we look at this problem from a maths point of view, it's quite simple if we see, well, we've got to break this X component into its vertical and horizontal components. So if that is my X, let's go down and find out what is its vertical and horizontal component. Well, this would be X sine of 60, because that's a 60-degree angle, and that's X cos of 60 degrees. Okay, so the vertical and the horizontal components, X sine 60, X cos 60. We're just looking at X, not Y yet. And if we know that this joint is in equilibrium, we know that the sum of the forces vertical are equal to 0, and the sum of the forces horizontal are equal to 0. So let's look at the vertical parts first. Sum of the forces vertical are equal to 0. That means this 270 going up minus the X times sine of 60 equals 0, because that's going to come down. And so therefore we can see that X is equal to 270 divided by sine of 60 degrees. And if you pull your calculators out, you'll find that that ends up being 311.77 newtons. So straight away we know that this force over here is 311 newtons. How do we find out why? Well, again, if we use the sum of the forces in the horizontal, This is a vertical force, that's a vertical force. The only horizontal force is this force going this way, so therefore y must be countering that force, because otherwise the whole bridge would be moving off to the left hand side. So y must be pulling back against this truss x. And so that if we add those all up, well, that is x cos of 60 degrees minus y. So y is going to be equal to, well, we know what x is now, we've just worked that out. X is 311, so 311.7 times cos of 60 degrees. And if we punch that into our calculators, we get 155.88 newtons. So we've effectively calculated both x and y using very, very simple maths, but the whole process came through this concept that if we take a bridge that's in equilibrium, each joint is also in equilibrium, and so we can isolate that joint and turn it into a simpler problem. I'll show you the graphical method in the next video.